All right, let's look at this next method of factoring. This is trinomial factoring using the constant term c, and this is when the leading coefficient is equal to 1. So when we have a trinomial in this form, so this is a second order equation such that the leading coefficient is equal to 1. Okay, so when this leading coefficient is equal to 1, then we're going to have a second order equation that's in this form. And here you can see that the variables b and c represent numbers. Okay, so it can be any number. So when you're presented with a trinomial in this form, this is how you factor it. So you look for two factors of the constant term such that if you add these two factors, they will sum up to this value, this coefficient b. And when that is successful, then the factorization of this trinomial will be x plus j, which was one of the two factors of the constant term, times x plus k. K was the other factor of the constant term. So, that's highly abstract. So let's look at this within the context of an actual example here. So in this example, we've got 5x to the fourth plus 10x cubed minus 75x squared. So right away, this presents us with a couple of problems. So first problem is, notice that this is technically a fourth order equation, which means that the variable has the highest power of 4, okay, to the exponent 4. And notice that this has to be like a second order equation. Okay, so that's the first problem. The second problem is that our leading coefficient isn't equal to 1. Our leading coefficient is a 5. All right, so we're going to have to do a little bit of work on this in order to get it in this form that it needs to be in order to apply this factoring method. So let's try and break down each of these terms, okay, into maybe a greatest common factor for each one. So the first term we could write as 5x squared times x squared. The second term, we could write this as 5x squared times 2x. Actually, you know what? Let's backtrack on this because I may be skipping ahead a little bit too fast. All right, so let's write this one out. So we've got 5 and we've got 4 x's. Then we've got 2 times 5 for 10, and then we've got 3 x's. And then with 75, we have 5 times 5 times 3. And then we've got 2 x's. All right. So what would be the greatest common factor that we've got? Well, each one of these terms has a 5 in it. Each of these terms has a single x in it. And each of these terms also has a second x in it. And so what do we have left in each term? Well, this one, we only have x squared left. In this second term, we have a 2 and an x. And in this third term, we have a negative 15. So what we've succeeded in doing is we've taken, kind of get rid of that, it's bothering me. Okay, we've taken this original fourth order equation here and we've factored it so that a part of it is factorable using this trinomial factoring form that we need. All right, so the challenge now is to try and find two factors of negative 15 that will add together to give us positive 2. So one of the easy ones we could do is we could say, well, negative 15 is the product of negative 1 and positive 15. That's true. But the problem is now, if we add these together, what we get is positive 14. Positive 14 is not positive 2. Okay, so a negative 1 and a positive 15 aren't going to work for us here. All right, instead what we could do is, what if we had a positive 3 and a negative 5? Well, that'll give us negative 15. And if we add those two together, what we get is negative 2. Okay, and negative 2 is not equal to positive 2. So we're a little closer, but we're not quite there. Well, what if instead of being a positive 3 and a negative 5, what if this was a negative 3 and a positive 5? Then if we add these two together, negative 3 plus 5, that does give us a positive 2, and those are equal. So now we found our two values, j and k, that when added together will sum up this value of b. So what that means is we should be able to write this trinomial in this form: x plus j times x plus k. And j is negative 3, and k is positive 5. So this is the factored form of that fourth order equation. Let's see here. I think I saw parentheses kind of fly away somewhere. Or I don't know where it went. Okay, so this is one example. And this is a good example because you're starting with an equation which doesn't fit the form right off the bat. So you're going to have to use, one of these previous factoring methods, this greatest common factor method first, in order to get this fourth order equation down to a second order with a leading coefficient equal to 1. All right. So let's look at this next example. So this next example is pretty much the same, except instead of it being an equation, or not an equation, but an expression with one variable, we have an expression in two variables. And variable x is to a second power, and variable y is also to a second power. Basically, the process is the same. But again, what we need is we need this to be, let's see here, second order for both. And the leading coefficient still has to be equal to 1. So this is for a trinomial that is in this form specifically. But just like before, we look at the coefficient in front of this y squared term, and whatever product we get for that coefficient, we want to make sure that those two factors can add up to give us the coefficient in front of the xy term. And if that's true, then this trinomial can be written as a product of these two expressions. So let's look here at this one, x squared minus 7xy minus 18y squared. All right, so let me go ahead and rewrite this. Now, this is nice because right off the bat, we can see that we're dealing with a second order equation, which is what we need. Both the x variable and the y variable are both to the second power, so that's good. And the leading coefficient has to be equal to 1. And we can see here that the leading coefficient in front of the x squared term is 1. So we're kind of good to go. So now we need to look at factors of negative 18. So to get negative 18, we could have negative 3 times positive 6. We could have positive 3 times negative 6. We could have negative 2 times positive 9. And we could have a positive 2 times a negative 9. And of course, we could have 1 times negative 18 and negative 1 times positive 18. Okay, let me go and write those down. All right, so we have to find a pair of these factors that will add up to give us negative 7. So right off the bat, these ones aren't going to work because that's going to, if we add those together, that's going to give us positive 3 and negative 3. So it actually looks like we're going to have to use this one because a positive 2 minus 9 will give us negative 7, right? Positive 2 times a negative 9. When those two are added together, that'll give us negative 7, and that equals the coefficient in front of this middle term. All right. So this is our value of j, and this is our value of k. So this expression can be written in this form, x plus jy times x plus ky. And let's see here, j is positive 2, and k is negative 9. So this positive here is going to turn into a negative, like that. All right, so this is the factored form of this original trinomial. All right, so one last thing to notice here that I didn't note before is, I guess it doesn't matter. Okay, yeah, no, that's it. So, here's, two different shapes or two different scenarios that you can apply this trinomial factoring to both, okay, equally. You just have to make a minor adjustment to the next step where you actually put the product of those, when you put those two expressions down, they're being multiplied together here. All right, so these are two examples. Next, I've got two think pair shares, so give those a try. And if you need some help with those, say, I think I've got the answers. Yeah, I got the answers down below. So if you don't get those answers, you can watch the next video for my solution to them. All right, let me know if you have any questions.